Our journey begins right here, on our home planet, Earth. Look up at the night sky. What do you see? A dazzling tapestry of stars, planets, and distant galaxies stretches out before us. As we venture further into space, we encounter breathtaking nebulae, the birthplaces of stars. These massive clouds of gas and dust are illuminated by the intense energy of young, hot stars. Our own galaxy, the Milky Way, is a barred spiral galaxy containing billions of stars. It's just one of billions of galaxies in the observable universe, each with its own unique story to tell. These are the enigmatic black holes. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape their grasp. They are formed from the remnants of massive stars that have collapsed under their own gravity. Imagine a star far more massive than our Sun, reaching the end of its life. As its nuclear fuel runs out, it can no longer support its own weight. The core collapses in on itself, creating a supernova explosion of unimaginable power. If the remaining core is massive enough, the gravitational collapse continues unabated. To understand the formation of a black hole, we must first journey to the heart of a dying star. Stars are not eternal. They have lifespans that depend on their mass. Stars much more massive than our Sun live fast and die young. These massive stars are fueled by nuclear fusion, a process where lighter elements like hydrogen fuse together to form heavier elements like helium, releasing tremendous energy. This energy creates outward pressure that counteracts the inward pull of gravity, keeping the star stable. However, this delicate balance cannot last forever. As the star ages, it gradually exhausts its hydrogen fuel. The iron core, now unable to generate energy, collapses under its own immense weight. This collapse happens in a fraction of a second, creating a shockwave that travels outward through the star. The shockwave slams into the star's outer layers, heating them to extreme temperatures and blasting them off into space in a cataclysmic explosion known as a supernova. For a brief moment, the dying star shines brighter than an entire galaxy, illuminating the cosmos with its final, brilliant light. Supernovae are among the most energetic events in the universe, scattering heavy elements forged in the star's core far and wide. These elements eventually become the building blocks for new stars, planets, and even life itself. When the collapsing core is massive enough, gravity overwhelms all other forces, including the pressure that keeps atoms from collapsing. The core continues to shrink, becoming denser and denser until it reaches a point of infinite density, a singularity. At this point, our understanding of physics breaks down. The singularity is thought to be a point of zero volume and infinite curvature of space-time. It is the heart of a black hole, hidden from view by the event horizon. The formation of a black hole is a dramatic and awe-inspiring event. Stellar mass black holes form when massive stars exhaust their nuclear fuel and collapse under their own gravity. These black holes are typically 3 to 10 times the mass of our Sun, yet they are incredibly compact. Imagine squeezing all the mass of 3 suns into a space smaller than a city. That's the incredible density of a stellar mass black hole. Despite their powerful gravitational pull, stellar mass black holes are not cosmic vacuum cleaners. They only consume matter that comes too close. While stellar mass black holes are impressive, they are dwarfed by their much larger cousins, supermassive black holes. These behemoths lurk at the centers of most, if not all, large galaxies, including our own Milky Way. Supermassive black holes are millions to billions of times more massive than our Sun. How these supermassive black holes form is still a subject of active research. One theory suggests they grow by gradually accreting matter from their surroundings, such as gas, dust, and even stars. Another theory proposes that they form from the mergers of smaller black holes. So far, we've explored black holes formed from the deaths of stars and those lurking at the centers of galaxies. But there's a third, more elusive type of black hole, primordial black holes. Primordial black holes, as their name suggests, are thought to have formed in the very early universe, shortly after the Big Bang. At that time, the universe was incredibly dense and hot, and tiny fluctuations in density could have led to the formation of black holes. Detecting primordial black holes is incredibly challenging as they do not emit any light of their own. Imagine yourself as a space traveler venturing closer to a black hole. As you approach this cosmic abyss, you would notice the fabric of space-time itself begin to warp and distort. Time would slow down for you relative to observers farther away, a bizarre phenomenon known as time dilation predicted by Einstein's theory of general relativity. At the heart of a black hole lies the event horizon, a boundary in space-time beyond which no information can escape, not even light. Once you cross this invisible threshold, you are forever trapped within the black hole's gravitational grip. At the very center of a black hole lies the singularity, a point of infinite density where the known laws of physics collapse. Here the immense gravity of the black hole crushes all matter, compressing it into an infinitely small point. Our current understanding of physics cannot fully describe what happens at the singularity. Some theories propose that the singularity might not be a point at all, but rather a ring or a more complex structure. Others suggest that the singularity might be a gateway to other universes or dimensions, although these ideas remain highly speculative. While black holes themselves are invisible, they often reveal their presence through the dramatic effects they have on their surroundings. One of the most spectacular phenomena associated with black holes is the formation of accretion disks. As matter falls toward a black hole, it rarely falls in a straight line. Instead, it spirals inward, forming a flattened disk of gas and dust known as an accretion disk. These disks can be incredibly hot and luminous, emitting intense radiation across the electromagnetic spectrum, from radio waves to X-rays. The intense gravity of the black hole accelerates the matter in the accretion disk to incredibly high speeds, causing friction and heating the disk to millions of degrees. For decades, black holes were thought to be inescapable cosmic traps, swallowing anything that crossed their event horizons and growing ever larger over time. However, in the 1970s, physicist Stephen Hawking made a groundbreaking discovery that revolutionized our understanding of these enigmatic objects. Hawking realized that black holes are not entirely black after all. They actually emit a faint thermal radiation, now known as Hawking radiation, due to quantum mechanical effects near the event horizon. This radiation, predicted by combining quantum mechanics with general relativity, has profound implications for the fate of black holes. Imagine a pair of virtual particles popping into existence near a black hole's event horizon. One particle falls into the black hole while the other escapes into space. The escaping particle carries away some energy from the black hole, reducing its mass ever so slightly. This process, known as Hawking radiation, causes black holes to slowly lose mass and energy over time. It's as if the black hole is evaporating away particle by particle, like a puddle of water slowly shrinking under the heat of the sun. The concept of virtual particles and Hawking radiation highlights the strange and counterintuitive nature of quantum mechanics. It suggests that empty space is not truly empty, but rather a seething cauldron of quantum fluctuations, constantly bubbling with the creation and annihilation of virtual particles. This quantum foam, as it is sometimes called, is thought to permeate all of space-time, even the seemingly empty regions between stars and galaxies. Hawking radiation, though incredibly faint and difficult to detect directly, has profound implications for our understanding of black holes and the universe as a whole. It suggests that black holes are not eternal, but have finite lifespans, eventually evaporating away and returning their energy to the universe. Warping reality, black holes and the fabric of spacetime. Black holes are not merely cosmic vacuum cleaners, they are profound disruptors of the very fabric of the universe. Their immense gravity warps spacetime, the four-dimensional continuum that encompasses everything around us. Imagine a bowling ball placed on a trampoline, causing the fabric to sag. Similarly, a black hole's mass creates a deep gravitational well in spacetime. This warping of spacetime has bizarre and fascinating consequences. Light, for instance, despite traveling at the fastest speed possible, is not immune to this distortion. As light passes near a black hole, its path bends, causing a phenomenon known as gravitational lensing. This bending of light allows us to observe objects that would otherwise be hidden behind massive objects like black holes. It's like looking through a cosmic magnifying glass, revealing the secrets of the universe lurking beyond our direct line of sight. But the warping of space-time goes beyond bending light. It affects the very flow of time itself. Time dilation, a cosmic consequence of gravity. One of the most mind-bending predictions of Einstein's theory of general relativity is that time is not absolute but rather relative, influenced by gravity. The stronger the gravitational field, the slower time flows. Black holes, with their extreme gravity, provide the most dramatic examples of time dilation. Imagine two identical clocks, one placed far from a black hole and the other placed near its event horizon. As time passes, the clock near the black hole would tick slower than the clock far away. This difference in time flow is not an illusion. It is a real, measurable effect. If you were to travel near a black hole and return, you would age less than someone who remained on Earth. You would have effectively traveled into the future. Time dilation is a profound consequence of the warping of space-time. It challenges our intuitive understanding of time as a constant and unchanging entity, revealing its intimate connection to gravity and the fabric of the universe. Wormholes and time travel. Through the looking glass of space-time, the warping of space-time by black holes leads to intriguing possibilities. One such possibility is the existence of wormholes, hypothetical tunnels through space-time. Imagine folding a piece of paper in half and poking a hole through both layers. That hole represents a wormhole, a shortcut through space-time. Theoretically, a wormhole could allow you to travel vast cosmic distances quickly. Some theories suggest black holes might act as entrances to wormholes. The concept of wormholes also raises the possibility of time travel. However, wormholes remain highly speculative with significant theoretical challenges. Beyond the veil, black holes as cosmic gateways. Black holes, with their extreme gravity and enigmatic singularities, have long captivated the imaginations of scientists and science fiction writers alike. They represent the ultimate cosmic unknowns, places where the laws of physics as we know them break down, and the very nature of reality seems to unravel. Could these enigmatic objects be more than just endpoints of stellar evolution? Some theories propose that black holes might be gateways to other dimensions or even other universes. Imagine a reality beyond our own, hidden from view by the veil of space-time. Could black holes be the key to piercing this veil and unlocking the secrets of these hidden realms? The idea of black holes as cosmic gateways is fueled by the extreme warping of space-time near their singularities. At these points of infinite density, the fabric of space-time is stretched and distorted beyond recognition, potentially creating tunnels or bridges to other regions of reality. While this concept remains highly speculative, it has captured the imagination of physicists and science fiction enthusiasts alike, inspiring countless stories and thought experiments about the nature of reality and the possibilities of cosmic exploration. String theory and extra dimensions, a glimpse into the unknown. String theory intersects with black holes, unifying all fundamental forces into a single framework. It proposes that the universe's building blocks are tiny vibrating strings. These strings vibrate at different frequencies, creating the particles and forces we observe. String theory predicts extra-spatial dimensions beyond our familiar three dimensions of space and one of time. These hidden dimensions could be crucial for understanding gravity and black holes. Black holes might interact with these dimensions, warping and distorting them. Their immense gravity could create gateways to other universes or regions of space-time. This hints at a universe far stranger and more complex than we ever imagined. Unraveling the tapestry, black holes as cosmic laboratories. Black holes, once science fiction, are now powerful laboratories testing our understanding of the universe. We've captured the first images of a black hole shadow, showcasing scientific ingenuity. Gravitational waves from black hole collisions offer new insights into the cosmos. These breakthroughs shift our understanding of the universe and our place within it. A universe of wonder, the everlasting quest. The study of black holes is a testament to human curiosity and our quest to comprehend the cosmos. We face profound questions about gravity, information, and the universe's destiny. What happens to matter as it falls into a black hole's singularity? Does it vanish, or is it preserved beyond our understanding? Can we harness black hole energy for future power? These questions are now at the forefront of scientific inquiry. The answers promise to revolutionize our understanding just as past discoveries did. The universe is a place of endless wonder filled with mysteries yet to be unraveled. Thank you for joining us on this journey through the universe's darkest mysteries. If you enjoyed this exploration, please like, subscribe, and share your thoughts in the comments. Until next time, keep looking up and stay curious.